The circle of fifths is one of the most important and fundamental concepts to Western music. It links every note in the chromatic scale in a sequence of successive fifths, starting and ending in the same given note. It's doubly important because, other than the unaltered chromatic scale itself, it's the only way to organize notes this way. There's no circle of seconds or thirds or anything. So, why is the circle of fifths unique? Well, it all comes down to math. To explain this concept, we have to abstract a bit. Instead of imagining a circle of fifths, think instead of any circle with any number of items in it. If you want to visit every item in the circle by moving by a certain number of spaces in a certain direction, the size of the step can't share any prime factors with the number of items in the circle. This, of course, includes every number that divides the number of items in the circle evenly. For example, if you move by 7 spaces along a circle with 20 items, you'll visit every item once without repeating, because 7 and 20 don't share any prime factors. In fact, 7 itself is prime. If a line is drawn that traces the path from point to point as you step, a star-like shape will be produced with each point corresponding to one item in the circle. However, if you pick a number that divides 20 equally, like 5, you'll see that the star will return to the starting item without having visited all of them. In fact, it only visited 4. The star is actually a square. If you want to visit every item, you would need to have 5 separate squares starting at 5 different points, which doesn't satisfy our initial criteria. Another thing to mention, moving by the total number of items minus the step length will create the same pattern as that step. As it relates to my first example, moving by 13 spaces will create the same pattern because 20 minus 7 is 13. 13 is equal to minus 7 in modulo 20, or more simply, moving by 13 steps clockwise is equivalent to moving by 7 steps counterclockwise. Thus, they create the same pattern, just in reverse. We can apply this knowledge to the chromatic scale, which contains all 12 notes used in 12-tone equal temperament. In order to create a sequence that visits every note once by jumping by a constant interval, the number of semitones in that interval can't share any factors with 12. Unfortunately, 12 has a lot of factors. In fact, it's known as a highly composite number because it has more factors than any positive number smaller than it. To illustrate this, let's go through all of its factors. First, 1. 1 isn't technically a prime number, so it doesn't share any prime factors with 12, and thus does create a sequence connecting every note. However, it's just the notes in order. This isn't any different than the chromatic scale, so we'll move on to 2. 2 and 12 share the prime factors too. Because 12 is 2 divided by 6, skipping by 12 creates a hexagon on the chromatic circle. In order to cover all the notes, you would need 2 hexagons. These 2 hexagons correspond to the 2 possible whole tone scales, because each note in the scale is 2 semitones, or 1 whole tone, apart. 3 also divides 12 evenly, creating a set of 3 squares on the chromatic circle. These 3 squares correspond to the 3 possible diminished seventh chords. 4 divides 12 into a set of triangles. These 4 triangles represent the 4 possible augmented triads, which contain 3 notes each. Now, finally, we get to 5. 5 is the first prime number that doesn't share any factors with 12, and is thus our first circle. However, you might have noticed that 5 semitones doesn't make a perfect fifth, but rather a perfect fourth. So, your boy messed up the title, huh? Well, not really. The perfect fourth and fifth are equivalent intervals. The circle of fifths can also be thought of as a circle of fourths, but in reverse order. This is also strengthened by the fact that the total of 12 semitones minus 5 semitones is 7 semitones, which is the interval of the perfect fifth. So, jumping by 5 or 7 leads to our circle of fifths. Doing so by the number between them, 6, creates 6 biangles, which represent the 6 possible pairs of tritones. Now, anything higher than 6 already has an equivalent jump. 5 and 7 are equivalent, as are 4 and 8, 3 and 9, 10 and 2, and 11 and 1. So, we've reached our conclusion. There's only 2 sequences of every note separated by a constant interval, the chromatic scale and the circle of fifths. However, this only applies in our current tuning system, which divides an octave into 12 equal pieces, known as 12-tone equal temperaments. In 24-tone equal temperaments, where every whole tone is divided into 4 instead of 2, there are 4 distinct circles. There's the circle formed by jumping by 5 quarter tones, which is between a second and a third, a circle formed by jumping by neutral thirds, which is 7 quarter tones, an 11 quarter tone circle, and of course, the 24-tet chromatic circle, which goes through each of those notes in order. Of course, there's still the circle of fifths and the 12-tone chromatic circle, but they no longer cover every note and exist in 2 variants each. Moreover, in tuning systems with prime divisions at the octave, like the popular 19 and 31-tone equal temperament, jumping by any interval will result in a circle because prime numbers, by definition, don't have any prime factors smaller than themselves. However, Using highly composite numbers as octave divisions can also be useful because it creates the possibility of dividing the octave evenly. Though each system has advantages and disadvantages, it's unlikely that 12-tone equal temperament and the circle of fifths are going anywhere anytime soon. If you enjoyed this video, please consider subscribing to my channel. Right now, I have some math videos in the works, but I'll definitely be making more videos about music theory.